Hello, so here is an exponential application. Okay, so we're going to look at a financial application, which is kind of money that you invest and you apply interest at certain times of the year or continuously. So there are two formulas that apply. So the first formula is used when the interest is compounded n times a year. Okay, so what this means, you have P is a principal, which is the initial amount that's put in a bank or an investment. A is the amount that you get a few years later. R is the interest rate in decimal form. N is how many times the interest is applied during a year, which is the compounding. And T is the number of years that the money is left in the bank or the investment. Okay, so N could be lots of things. So N is 1 if it's compounded annually. N is 2 if it's semi-annually. N is 4 if it's 4 times a year, which is quarterly. N is 12 if it's 12 times a year or monthly. And N equals 365 if it's compounded daily, every day. Right? So the compounding is like, all right, you have a amount of money in the bank, and say if it's monthly, at the end of each month, they go, oh, let's apply the interest. Let's calculate the interest, and that interest is going to be a certain amount of money, which gets added to your balance in the bank. The next month, the interest is applied again to this new amount. So interest is applied every month at the end of the month, and then the money accumulates. Or if it's annually, the interest is just applied at the end of the year. All right? The second formula is continuous interest, compounded continuously. So the interest is applied not every day or every month and every year, but every millisecond. Okay, and then that formula is given by A equals P e to the RT, so E the natural exponential base. All right, so let's look at this example here to kind of see how those formulas are useful. Jermel's parents put $10,000 in investments for his college expenses on his birthday. They hope the investment will be worth $50,000 when he turns 18. All right, so let's see, they started on his first birthday when he turns 18, so that will be T equals 17 years. All right. If the interest compounds continuously, approximately what rate of growth will they need to achieve this goal? Okay, so you can see the interest is applied continuously, which means we're going to use that second formula. A equals P e to the RT. Now we're going to plug all the numbers that we know. So it says that they put $10,000 in the bank. That's the P value. After 17 years, so T is 17, they're going to get $50,000, or they want $50,000, so that's A, that's the amount. And it's asking for the rate of growth. It's asking for the R value, or the annual interest rate. Okay, so we're going to put 50,000 here, 10,000 here, e to the R times 17, and now we need to solve this. Okay, so this is an exponential equation. We're going to need to take natural log of both sides, but first we're going to divide both sides by 10,000 to make the exponential part all by itself. All right, so 50,000 divided by 10,000 is 5 equals e to the 17r. Now take log of this and log of that. The natural log cancels the e's, they are inverses of each other. So we get ln of 5 equals 17r. Divide both sides by 17. So r equals log of 5 divided by 17. Now we plug this in the calculator. Alright, so we're going to do ln of 5 divided by 17, 0.095. 0.095. Okay, so that's the interest rate in decimal form. If I change it to percentage form, you multiply this by 100, so you get 9.5%. Okay, so this is the annual interest rate that they need to find in order to get the amount that they want when he turns 18.